Module 5. Lecture A. Defining functions. By the end of this lecture, you will be able to define simple Python functions using def with clear names and parameters. Use return statements to send results back from functions. And call functions with appropriate arguments and interpret their outputs. Python function syntax using the def keyword. When you define a function in Python, you start with a special keyword that tells the interpreter a new function is being created. This keyword begins a block of instructions that you can name and reuse whenever needed. It announces the action, its name, and what information it requires, such as for calculating a shopping cart total or converting temperatures. The function's header and body are then organized around this initial declaration. In Python, the keyword used to define a function serves two main roles. It marks where a function definition starts and helps you visually separate defining a function from later using it. Right after this keyword, you write the function's name and a set of parentheses that may list parameters, which describe the inputs the function expects. This first line is called the function header and summarizes the function's name and inputs. Everything indented beneath the header forms the function body, where the actual steps of the task are carried out. When you define a function in Python, you are creating a set of instructions for a task, not running the task yet. The special keyword used to define the function appears only at this setup stage, not when you later call and use the function. This distinction helps you see the difference between introducing new behavior and reusing existing behavior in your programs. Understanding this makes it easier to read and write Python code efficiently. Whether you are working with financial data, survey results, or sensor information. Python code using the def keyword. In this lesson, you will see how to use the def keyword to create simple functions and how defining a function is different from calling it. We will first define functions using def, which sets up what the function does but does not run it yet. Then, we will call these functions with example values to actually perform their tasks. Finally, we will print the results of these function calls so you can clearly see the output produced by the defined functions. This line in the script is a placeholder indicating where you would install any required libraries before running the code. It reminds you to use your package manager to add a library if it is not already available in your environment. Doing this first is a common way to make sure all dependencies are installed and the script can run without errors. We define a function that converts a measurement in inches to feet. It takes an input value in inches and divides it by 12, since 1 foot equals 12 inches. The result of this division is stored as the value in feet. The function then returns this feet value to the place where it was called, providing the converted measurement. We define a function called greetUser that takes one input, which is the person's name, as text. Inside the function, we build a message by joining the word hello with the given name and an exclamation mark. This creates a personalized greeting. The function then returns this greeting so it can be used elsewhere in the program. We use a function that converts inches to feet by dividing the number of inches by 12. In this example, we pass in 36, and the function computes how many feet that equals. The result is stored in a variable and then used to print a message stating that 36 inches is equal to that number of feet. This produces a clear, readable description of the conversion. We call a greeting function and pass in the name Alex as its input. Inside the function, a greeting message is created by joining the word hello, the given name, and an exclamation mark. The function then returns this complete greeting message. Finally, we print the returned message, which shows hello, Alex, with an exclamation mark on the screen. This script shows how to define and use simple functions in Python. One function converts a measurement from inches to feet, and another creates a greeting message. When the code runs, it converts 36 inches to 3 feet and prints the result, then creates and prints a greeting for the name Alex. Overall, it highlights the difference between defining functions and calling them, and how to return and display the results of those calls. Naming functions clearly. When you name a function, choose a clear, descriptive name that states what the function will do, almost like finishing the sentence, "This function will." A function that calculates average temperature should have a name that makes that purpose obvious, not a vague label. Likewise, a function that checks login details should sound like it verifies credentials, not use a cryptic or misleading title. Names that reflect a function's action or result make your code easier to read, debug, and reuse. When naming functions, keep each one focused on a single, clear task so its name is easy to choose and understand. This focus makes it obvious what the function does and also reveals when a function is trying to do too much. If you struggle to give a function a simple, descriptive name, that is often a sign it should be split into smaller, more specific functions. Using this approach helps keep your program's structure and logic organized and easier to maintain. Clear function names are essential for working effectively with code, both in teams and on your own. When functions are named to clearly reflect what they do, such as recording activities or generating reports in a health app, others can quickly understand the system without reading every detail. These names also make it easier to return to the code later to fix bugs or add features because they guide you to the right places and reduce confusion. Building the habit of using clear, descriptive names early on will pay off as your projects grow more complex over time. Python code, naming functions clearly. This material explains how to choose clear, descriptive names for functions using simple, everyday examples. It contrasts vague names with more specific ones for the same basic tasks, so you can hear how much easier the descriptive versions are to understand. The goal is to show that with good names, you can often tell what a function does without reading its internal code. Overall, clear naming makes programs easier to read, reason about, and maintain. This line is simply a placeholder comment indicating where a command to install a required library could be added if the script ever needs one. It reminds developers to make sure all dependencies are available. In the current version of the script, no installation is necessary, but the comment keeps the code ready and clear for any future additions. Consider a function with a vague name that takes two distances in miles. adds them together, and returns the total distance. Technically, the function works correctly by summing its two inputs. However, because its name does not clearly describe this purpose, it is hard to know what the function does without looking inside it. This example shows how unclear naming can hide a function's intent and reduce code readability. We define a function with a clear descriptive name that adds two trig distances measured in miles. It takes two distance values as input, adds them together inside the function, and returns the total distance. Using a clear name makes it easy for someone reading the code to understand that the function's purpose is to combine two trig distances without needing to examine its internal steps. We define a password checking function that evaluates whether a password is strong. It takes the password text as input and first checks if its length is at least 8 characters. It then checks whether the password includes at least one numeric digit by examining each character. The function returns true only if both the length and digit requirements are satisfied, and false otherwise. We define a function that checks whether a password is strong by applying two main rules. It first verifies that the password has at least 8 characters. It then scans through each character to see if there is at least one numeric digit. The function reports that the password is strong only when both the length and digit requirements are satisfied. Otherwise, it reports that the password is not strong. This example prints a message to the console that includes the result of calling a function with a vague name. The function, called doStuff, takes two distances in miles and adds them together. In this case, it adds 12 and 8 to get 20. The point is to show that even though the function works correctly, its unclear name does not reveal its real purpose of adding two distances. We use a clearly named function that adds two trig distances measured in miles. It is called with the values 12 and 8, which it sums and returns as the total distance. We then print a message to the console along with this result, stating that it is the outcome of the clear distance function name. This makes it easy to understand what the function does without needing to see how it is implemented. This example shows code that checks password strength using a function with an unclear, vague name. The function tests whether a password is strong enough by requiring at least 8 characters and at least one digit. The password pass1234 is given to this function, and the result of the check is printed. The printed output also notes that a vague function name was used. We use a clearly named function called the strong password checker to evaluate whether a given password is secure. It takes a password, such as pass1234, and checks if it meets basic rules like having at least 8 characters and including at least one digit. The result of this check is printed to the console with a clear label. This example shows how a descriptive function name makes the purpose of the code easy to understand. This script shows why clear function names matter by comparing vague names with descriptive ones for two simple tasks. One pair of functions adds two trig distances in miles, and another pair checks whether a password is strong. Both versions of each function produce the same results. The distance functions return 20 miles, when given 12 and 8, and the password functions agree that the example password is strong because it is long enough and includes a digit. The key point is that descriptive names make it easier to understand what the code does without looking inside the functions. Indenting function bodies. In a function definition, indentation is a key part of the syntax because it shows which statements belong to the function. The interpreter treats all lines that are indented under the function header as part of that function, and anything aligned with the left margin as outside it. In practice, this means every step the function performs must be consistently indented so the interpreter knows they are all within the same block of code. Consistent indentation inside a function is essential for both correctness and clarity. Misaligned lines can cause the interpreter to misunderstand the structure of the code, which may lead to unexpected behavior. In a function that processes survey responses, for example, a step that is not properly indented might not run as intended and create subtle errors. By keeping all related statements at the same indentation level, you help ensure the function works predictably and is easier to read and understand. Indentation in a function is used to visually group related code so you can see which parts belong together. When you write conditions or loops, extra indentation shows which actions only run in certain cases or are repeated. For instance, in a hotel booking function, the steps to reserve a room and send confirmations would be indented under the checked for room availability. This layered structure reflects the logic of your algorithm and makes the code easier to read, debug, and expand. Python code. Indenting function bodies. This material focuses on using indentation to clearly show which steps are grouped together inside a function. It also emphasizes how nested indentation can visually indicate blocks of conditional logic within that function. Finally, it highlights printing output that makes it obvious which lines of code are running inside the function body. This line is a placeholder comment indicating where you would add a command to install a required library for the script. It serves as a reminder to make sure any external dependencies are installed before running the code. Including such comments is a common practice in Python projects to prevent runtime errors caused by missing packages. We define a function called calculateTotalCost dollars that takes an item price in dollars and a tax rate in %. Inside the function, we find the tax amount by multiplying the price by the tax rate divided by 100. We then add this tax amount to the original price to get the total cost, including tax. The function returns this total cost so it can be used elsewhere in the program. We define a function that takes an item price in dollars and a tax rate in %, then calls another function to calculate the total cost, including tax. The function checks whether this total cost is greater than 50, and if so, prints a message that it is a large purchase along with the total cost. No matter what the total is, it always prints a message that the purchase has been processed, again, including the total cost. This example shows how indentation groups lines of code inside a conditional so that only certain statements run when the condition is true, while others run every time. The describe purchase dollars function is called with the values 60 and 8 to calculate the total purchase cost, including tax. Inside it, another function computes this total by adding tax to the item price and stores the result. The code then checks whether this total cost is greater than 50, and if so, prints a message that it is a large purchase along with the total amount. In all cases, it prints a final message confirming that the purchase has been processed and shows the total cost. This script uses two functions to handle a purchase with tax. The first function calculates the total cost by adding tax to the item price. The second function checks whether this total is more than $50, and if so, prints a message about a large purchase, then always prints the total cost. When run with a $60 item and an 8% tax rate, both messages appear because the total is over $50. This example shows how indentation determines which lines run inside functions and conditional blocks. Function parameters basics. Positional parameters explained. In a function, positional parameters are inputs that are matched by the order in which values are passed. The first argument goes to the first parameter, the second to the second, and so on, and the function uses these ordered inputs to do its work and produce a result. If you change the order of the arguments, the function may still run, but it will use the wrong data and give incorrect output. Understanding this rule about order is essential for both designing functions and correctly interpreting their results. When a function expects inputs in a specific order, such as weight first and height second for calculating body mass index, the position of each argument is critical. If you accidentally swap the order, the function will still run and produce a number, but that number will be wrong because the inputs were misinterpreted. This example shows that with positional parameters, the accuracy of any calculation depends directly on providing arguments in the correct sequence. Positional parameters are important when using functions that produce complex results because the order of inputs directly affects the output. For example, in a travel booking function, mixing up the departure city, arrival city, and travel date can return a fare for the wrong trip. In a grading system, swapping a student's score with the maximum score can produce an incorrect percentage. These situations show that a function's accuracy depends on providing its inputs in the correct order. Python code, positional parameters explained. This material explains how positional parameters control what a function does and what values it returns. When arguments are passed in the correct order, the function produces meaningful numeric results. If the arguments are swapped, the function may still run and return numbers, but those results will be incorrect even though they look valid. The examples rely only on standard Python features and do not require any external libraries. We define a function called miles per gallon that takes two inputs, the miles driven and the gallons of fuel used. Inside the function, we compute the fuel efficiency by dividing the miles driven by the gallons used. This calculation gives the distance the vehicle can travel per unit of fuel. The function then returns this value so it can be used elsewhere in the program. When we call a miles per gallon function, we must pass the miles driven first and the gallons used second so it can compute the result correctly. For example, using 300 as miles and 10 as gallons gives a meaningful value. If we reverse the order and pass 10 as miles and 300 as gallons, the function still runs but produces a misleading result. This shows that keeping the correct positional order of arguments is essential for reliable calculations. The example first shows the correct order of arguments for a function that computes miles per gallon. Entering 300 miles and 10 gallons gives 30 miles per gallon, which is the expected result. It then shows what happens when the arguments are reversed. Entering 10 miles and 300 gallons produces a much smaller value of about 0.033 miles per gallon. This contrast emphasizes that keeping the correct positional order of arguments is essential for getting reliable results from the function. This example shows why the order of positional parameters in a function call matters. When you change the order of the arguments, the function still runs, but it produces different results. This difference highlights that functions expect arguments in a specific sequence. To get reliable and meaningful output, you must pass values in the correct order. This script shows why the order of positional parameters in a Python function matters. It uses a function that calculates miles per gallon from miles driven and gallons used. When the arguments are passed in the correct order, the result is a reasonable value of 30 miles per gallon. But when the order is reversed, the function produces a meaningless value of about 0.033 miles per gallon. This example emphasizes that using the correct argument order is essential for accurate and reliable function results. Using default parameters. Default parameters let a function use a fallback value when some inputs are not provided, so the function can still run smoothly. They act as the function's own choice of value when no specific instruction is given. This is especially useful for functions with typical behavior that usually stays the same, such as calculating a final price using a standard tax rate. By setting a default tax rate, you can call the function with just the item price, but still change the tax when needed. Overall, default parameters make functions more flexible and easier to use without requiring every detail each time. When working with default parameters in a function, it is important to understand that any argument you explicitly provide will override the default value. If you do not supply an argument, the function simply uses its default. This behavior keeps the function's logic consistent and its output predictable. For instance, a name formatting function might use a casual style by default, but switch to a formal style when that option is specified. So the result always reflects either the caller's choice or the sensible default you designed. Default parameters help you design functions that behave sensibly in typical situations, while still allowing flexibility for special cases. A good default makes the function's output feel natural and reduces the need for users to constantly tweak settings. For example, a function that summarizes an article might default to a medium-length summary with options for shorter or longer versions, and a logging function might default to essential information, with an option for more detailed diagnostics. By choosing such defaults carefully, you make functions easy to use in everyday work while keeping them adaptable when more control is needed. Python code. Using default parameters. This section explains how to use simple function default parameters and what happens when you omit an argument. when a parameter has a default value and you do not provide that argument in a function call, the function automatically falls back to the default. You then compare calls that rely on these default values with calls where you explicitly pass your own values to override them. If needed, you may first install any required library using the appropriate package installation command. There is a function called calculateFinalPrice that takes a price in dollars and a tax rate in percent. The tax rate has a default value of 8%. This means that if no tax rate is given when the function is used, it automatically applies 8% tax. If a different tax rate is provided, the function uses that instead to compute the final price. To use a tax rate in calculations, we first convert the percentage into a decimal by dividing it by 100. This step is needed because percentages are not directly usable in arithmetic operations. Once converted, the decimal value acts as a multiplier that we apply to a price to find the tax amount. The code finds the tax amount by multiplying the item's price in dollars by a tax multiplier. This multiplier represents the tax rate in a form that can be applied directly to the price. The result of this multiplication is the exact amount of tax added to the original price. This function calculates the final price by adding the original price in dollars to the tax amount. In other words, it takes the base cost, computes the tax, and then combines them. The result is the total cost the customer pays, including tax. We call the function that calculates the final price using only a price of $50. Because we do not specify a tax rate, the function automatically uses its default value of 8%. This shows how default parameters are applied when an argument is left out. The function then prints the final price with the default tax included. In this example, we call the function that calculates an item's final price, but we supply our own tax rate instead of using the default. We pass in a price of $50 and a tax rate of 5% as two arguments. Providing this second value overrides the function's built-in tax rate. The function then computes the final price using this custom tax and prints the result with a label indicating that a custom tax rate was used. We define a function called makeGreeting that takes two inputs. The first input, called nameText, is required and holds the name of the person to greet. The second input, called greetingWord, is optional and has a default value of hello. This means the function can either use a custom greeting word if one is provided, or automatically use hello when no custom word is given. The function then combines these inputs to create a greeting message. The code builds a personalized greeting message by combining a greeting word with a person's name. It uses a formatted string to place the greeting, then a comma, then the name, and finally an exclamation mark. This creates a complete greeting sentence. The greeting word can be the default option or a custom one if the user provides it. The function returns the full greeting message it has built, combining the chosen greeting word, whether default or custom, with the person's name. By using a return statement, this complete message is sent back to the place where the function was called. This allows the greeting to be used, stored, or displayed as needed in the rest of the program. This example calls a function that creates a greeting message using the name Alex as input, while relying on the default greeting word, which is hello. Because no custom greeting word is provided, the function uses its built-in default and produces the message, "Hello, Alex." This message is then generated and printed. The example shows how default parameters work when a function is called without specifying all of its possible inputs. In this example, we call a function that creates a greeting message by passing in the name Alex and choosing the greeting word welcome. This custom greeting word replaces the function's default greeting, which is hello. The function then combines the chosen greeting with the name to form the message welcome Alex. Finally, this message is printed to the console, showing how you can change the greeting by providing a different word when you call the function. This script shows how default parameters work in Python functions. It uses a price calculation function with a built-in tax rate of 8%. Then demonstrates that you can override this by providing a different tax rate, such as 5%, to change the final price. It also includes a greeting function that normally says hello to a given name, but can be customized to use a different greeting word. Together, these examples illustrate that default parameters let you define standard behavior, while still allowing flexible, customized function calls, without changing the function itself. Argument order. When calling a function that takes several parameters, the order of the arguments matters a lot. Positional parameters are matched by their position, so if you change the order, each parameter may receive the wrong value. The function will usually still run, but its result can be wrong. For example, if a function calculates a test score percentage, and you accidentally swap the total points and the earned points, the calculation will be incorrect. Therefore, you must keep the argument order correct to ensure accurate results. When a function uses both required positional parameters and parameters with default values, the order of the arguments matters. You must always supply the required arguments first in the order they are defined, and only then provide any that have defaults. If you ignore this order, you can accidentally override default values or fail to supply required inputs. This can lead to errors or confusing results, such as a formatted purchase message where the customer name, item, and greeting no longer make sense. Respecting argument order ensures the function produces clear and meaningful output. When designing functions that return values, treat the order of arguments as a strict contract between the function and its caller. The function expects inputs in a specific sequence so it can produce correct results. In real applications like financial processing or data logging, mixing up this order can create results that look reasonable but are actually wrong, which is especially dangerous. To reduce this risk, programmers rely on clear naming and, when possible, named arguments. But even with positional arguments, carefully maintaining the correct order is essential for accurate behavior. Python code, argument order. This lesson shows how changing the order of arguments in a function call can change the value the function returns. It explains how positional parameters work, including a mix of required and default parameters. You will see printed results that let you compare correct argument ordering with incorrect ordering, so you can clearly observe the impact on the function's output. This comment explains that the script only uses Python's built-in standard libraries. so it does not require installing any extra packages. It serves as a reminder that additional libraries could be added if needed in the future. For now, the existing standard tools are enough for the code to run as intended. We define a score percentage function that takes two inputs, the points earned and the total possible points. This function calculates the percentage score by dividing the points earned by the total points. It then multiplies that result by 100. The final value tells us what percent of the total points was earned. We call the score percentage function with the points earned first and the total possible points second, for example, 45 and 50. The function calculates the percentage by dividing the earned points by the total points and multiplying by 100. This result is stored in a variable for the correct percentage. Finally, we print this value with a label that indicates the arguments were passed in the correct order, ensuring the calculation is accurate. In this example, the score percentage function is called with the values 50 and 45 in the wrong order. As a result, the function treats 45 as the total points and 50 as the points earned. This makes the earned points greater than the total, so the calculated percentage is more than 100. When this incorrect percentage is printed, it clearly shows why keeping the correct order of arguments in function calls is important. This function creates a personalized purchase message using the customer's name, the item's name, and an optional greeting. If no greeting is given, it automatically uses hello. It then combines these pieces into a friendly sentence, such as, "Hello, Alice, enjoy your coffee mug." This design keeps the message flexible while still providing a useful default greeting. We call the purchase message function with the customer name Alice and the item coffee mug, which uses the default greeting of hello. The function builds a message by combining the greeting, the customer's name, and the item name. It returns the sentence, "Hello, Alice, enjoy your coffee mug." We then print this as the correct order message to confirm that the arguments were passed in the right order and produce a clear, coherent result. In this example, the purchase message function is called with its two arguments in the wrong order. The word welcome is passed where the customer's name should go, and Alice is passed where the item name should go. Because the function interprets the first argument as the customer and the second as the item, it produces a confusing message. This incorrect result is stored and then printed, demonstrating how swapping argument order can lead to unexpected and misleading output. We call a function that creates a purchase message, setting the customer name to Bob and the item to a notebook. Instead of using the default greeting, we explicitly pass the word greetings to replace it. This shows how a default parameter can be overridden by providing a new value. The function then returns a personalized message, which we print to the console to confirm that the greeting has been successfully customized. This example shows how the order of arguments in a function call can change the result. When calculating a score, using points earned divided by total points gives a reasonable percentage, but reversing the order produces a value over 100%, which is incorrect. A second function builds a purchase message with a default greeting, and it works as intended when the customer name and item are passed in the right order. If the arguments are swapped, the function treats the greeting as the name and creates a confusing message. The example also shows that you can override the default greeting by explicitly providing all arguments, which produces a personalized message while still relying on correct argument order. Understanding return values. Using return values. When you call a function, its main purpose is to produce a return value, which is the result it gives back after doing its work. You provide inputs, the function processes them, and then returns an output your program can use. This return value is important because it lets your program make decisions, display information, or start other actions. For example, a function might return the total cost of a shopping cart or indicate whether a student passed a course, and that returned value can then be used throughout the rest of your program. When a function returns a value, you need a plan for how to use it. Often, you store the result in a variable so you can reuse it later, such as saving an estimated project duration to compare with deadlines or combine with other data. You can also use the return value immediately in calculations or in conditional checks that guide program decisions. The main idea is to capture and apply these returned values so your program becomes more flexible and powerful. When you call a function, it is important to understand exactly what value it returns and what that value means. A function might give back a score, such as a customer satisfaction rating, or a simple result, like whether login access is granted. Knowing the meaning and possible range of these values helps you decide how your program should respond, such as what message to show or how to adjust its behavior. If you misunderstand the return value, your program can behave incorrectly, so always be clear about what is returned and how it controls the flow of your code. Python code using return values. This material focuses on using function return values effectively in simple, beginner-friendly programs. It shows how to store returned values in variables so they can be reused flexibly later in the program. It also demonstrates how to use returned values directly inside expressions, such as calculations, and inside conditional checks to control decision-making. Only standard libraries are needed, so no extra installation is required. We define a function called calculateTotalPrice that takes a subtotal in dollars and a tax rate in percent. Inside the function, we find the tax amount by multiplying the subtotal by the tax rate and dividing by 100 to convert the percent to a dollar value. We then add this tax amount to the original subtotal to get the final total price. The function returns this total price so it can be used elsewhere in the program. The ProjectFitsSchedule function checks whether a project can be finished within the time available. It takes the estimated hours needed for the project and the total hours available. It then compares these two values and returns a true or false result. If the estimated hours are less than or equal to the available hours, the function returns true, meaning the project fits within the schedule. Otherwise, it returns false. We start by setting the cart subtotal to $45, which is the amount before tax. Then we define the sales tax rate as 8%, to calculate how much tax to add. We call a function that uses the subtotal and tax rate to compute the final price including tax. The result is stored in a variable representing the cart total, so it can be used later in the program for more calculations or for display. This code prints a message to the console that tells the user the final cost of their shopping cart. It uses the total price that was already calculated, including sales tax, and combines it with a short descriptive message. The result is a clear statement of the total amount the user needs to pay in dollars. Set a shipping fee of $5. Then add this fee to the existing cart total to get the grand total. This combined amount represents the full cost, including shipping. Finally, display the grand total with a clear message showing the total in dollars. This method lets you easily update the overall cost when additional charges like shipping are applied. We begin by setting the estimated hours needed for the project to 12 and the available weekend hours to 10. We then call a function that checks whether the project can be completed within the available time. Using these two values as inputs, the function returns a true or false result, which we store in a variable indicating whether the project fits the schedule. This result tells us if the project can be finished within the given time frame. The program uses a true or false value to decide whether the project fits within the available weekend hours. If the value indicates that it fits, the program prints a message saying the project fits the schedule. If not, it prints a message that the project does not fit the available hours. This conditional check lets the program report to the user whether the project timeline is feasible. This script shows how to use function return values in Python for both calculations and decisions. It first calls a function to add sales tax to a subtotal, stores the return total, and prints it. Then it adds a shipping fee to that total and prints the final amount. The code also calls another function that compares estimated project hours to available hours and returns a true or false value. Based on this result, it prints a message indicating whether the project fits into the schedule. Overall, it demonstrates how returned values can be stored in variables and then used in further computations and conditional checks. Return values none. When you call a function, it either returns a value you can use or it does not, and this is important for understanding how your program behaves. A function that returns a value takes input and produces a result you can store or pass to other parts of the program. A function that does not return a value simply performs an action and does not give you a meaningful result to work with. In Python, these action-only functions automatically return a special placeholder called none, which signals that there is no useful output. Knowing this distinction helps you decide whether to expect a result or just an action when you call a function. Some functions in a program return a useful value, such as a discount amount you can apply to a price, display to the user, or store in a database. Other functions only perform an action, like printing a confirmation message, and do not return a value you can reuse. If you try to treat the result of an action-only function as a number or piece of text, you will run into problems because it actually represents no result. Knowing which functions produce reusable values and which only carry out actions helps you use them correctly in your code. When using functions in calculations or combining their results, you must know whether each function returns a value or only performs an action. If you treat a function that returns nothing as if it produced a real value, your program can behave unpredictably or even crash. To avoid this, be clear about each function's purpose, whether it computes a result you can use or just causes a side effect, such as logging or updating something. With this understanding, You can safely chain functions and interpret their outputs correctly, keeping your programs robust and easier to understand. Python code. Return values versus none. This script demonstrates the difference between functions that return a value and those that return nothing or none. It shows that when a function returns a value, that result can be easily reused in later calculations. It also illustrates what happens if you mistakenly try to use a result that is none, highlighting why understanding return values is important. This comment line suggests installing a required library if needed, but also makes clear that this particular script does not actually need any external libraries. It serves as a placeholder to show where dependency information would go. By including it, the author signals that the script is self-contained and helps users quickly understand that there are no additional installations required. We define a function called calculateDiscount that computes how much money is taken off a purchase based on the total price and a discount percentage. Inside the function, the discount amount is found by multiplying the total price by the discount percentage and then dividing by 100. This converts the percentage into a dollar value. The function then returns this discount amount so it can be used in other calculations. We define a function called printConfirmation that takes two inputs, an order identification number and a customer name. Inside this function, it prints a message confirming that the order with that identification number for that customer has been received. The function's purpose is to perform this action of printing feedback for the user. It does not return any value because it is not meant to produce a result for further computation. We begin by setting the order total to $120, which represents the starting amount before any discounts are applied. Defining this starting value lets us easily refer to it later in our calculations. From there, we can adjust the total by applying discounts or computing the final amount owed. We use a discount calculation function by giving it the total order amount and the discount percentage. Inside this function, the discount is found by multiplying the total price by the percentage and then dividing by 100. This gives the discount amount in dollars. We store that result in a variable so we can use it later, for example, to reduce the final total price. To get the final total after a discount, subtract the discount amount from the original order total. This calculation gives you the price the customer actually needs to pay. You then store this final value so it can be used later, such as for further processing or displaying to the user. We now display the final total after applying the discount. This total uses the previously calculated discount amount to adjust the order cost. As a result, the customer sees the correct amount they need to pay. The message clearly shows this final total in dollars, so the outcome of the discount calculation is easy to understand. In this example, we call a function that prints a confirmation message using the order ID and customer name. The function is only meant to perform this action and does not return a value. When we try to store the result of this function call in a variable, that variable ends up holding the special Python value, none. This shows what happens when a function carries out a task but does not explicitly return anything. we print a message that shows what the confirmation function returns, and in this case, it returns the special value none. When we include the result of calling this function in the printed message, the output clearly displays that the result is none. This happens because the function does not explicitly return any value, so its return value is automatically set to none and shown as such in the output. In this example, we try to add a number to a value that is none inside a try block so we can handle any errors safely. This operation is expected to fail because none cannot be used in arithmetic with numbers. If it did not fail, the program would print an incorrect total, but that situation is unlikely. Instead, a type error occurs and the except block catches it. The program then prints an error message explaining that the failure happened because it attempted to treat none as a number. This script shows the difference between functions that return values and those that do not. First, it defines a discount calculation function that returns a number, which is then used to compute and print a final total, demonstrating how returned values can be reused in later calculations. It then defines another function that only prints a confirmation message and returns nothing, which in Python means it returns the special value none. When the script tries to use this none value in a calculation, it causes a type error that is caught and printed. This illustrates why it is important to understand what a function returns before using its result in arithmetic. Returning multiple values. Functions do not have to return just one value. They can return several related results at the same time. For example, a function that analyzes exam scores might give you the average, the highest score, and the lowest score in one call. In this case, the function returns a structured result that acts like a container holding multiple pieces of information. Your job as the programmer is to unpack that container correctly and use each part as needed. Understanding this idea helps you design more useful functions and work with their outputs more effectively in your programs. When using a function that returns multiple values, you must know both how many values it returns and the order they come in. Each position in the output corresponds to a specific meaning, so you should read the documentation and assign the results to variables in the correct sequence. If you only need some of the values, you can ignore the rest, but you still need to understand what each position represents. This careful matching helps prevent mistakes and keeps your code clear and correct. When a function returns multiple values, you need to understand what each value represents and how they relate, so you can use them correctly in your program. For example, a function might return several pieces of weather data or several financial details, and you may pass some of these to other functions, display them, or use them in decisions. The key is to design functions so their outputs are predictable and clearly documented. This makes it easier to follow how information moves through your code and to understand the results your program produces. Python code returning multiple values. This section explains how to return multiple values from simple, beginner-friendly Python functions and how to work with those values when calling the function. You learn that a function can send back several results at once, and the caller can unpack them into separate, clearly named variables. The narration highlights that the order of these returned values matters, because each position is assigned to a specific variable. It also shows how you can selectively ignore any returned values you do not need while still correctly receiving the ones you do. This line is a placeholder comment reminding you to add a command to install any required external library before running the script. It helps ensure that all necessary dependencies are available so the code runs correctly. Including such reminders improves code portability and makes it easier to share or deploy the script in different environments. We define a function that converts a total number of inches into miles, feet, and inches. It first finds the whole number of feet by dividing the total inches by 12 and ignoring any remainder. It then uses the remainder from this division as the leftover inches. Next, it computes miles by dividing the total inches by 63,360 using regular decimal division for accuracy. Finally, the function returns all three results together so they can be easily unpacked into separate values. We begin with an input of 1,000 inches that we want to convert into miles, feet, and inches. A conversion function is called with this input and returns three values representing these units. We store each returned value in its own variable, then announce the original number of inches being converted. Finally, we print the miles value rounded to 4 decimal places, followed by the feet and remaining inches, each clearly labeled so the results are easy to understand. We set a short distance in inches to 25 and pass it to a conversion function that returns miles, feet, and inches. In this case, we only care about the feet and inches, so we ignore the miles value using a placeholder. We then print a message showing the original inches converted into feet and inches. This example illustrates how to unpack only the specific results you need from a function that returns multiple values. This script shows how a Python function can return several values at once and how to unpack them. The function converts a total number of inches into miles, feet, and remaining inches, and the first example prints all three values, with miles rounded to 4 decimal places. In the second example, the function is called again, but the miles value is intentionally ignored so that only feet and inches are used. Together, these examples highlight that the order of returned values matters and that you can choose to ignore values you do not need when unpacking a function's result. In this lecture, you learned to define simple Python functions using def with clear names and parameters, use return statements to send results back from functions, and call functions with appropriate arguments and interpret their outputs. In the next lecture, Lecture B, we will go over using functions well. Thank you for your attention. See you all in the next lecture.